Physics lesson with Mr. M. In this video lesson, I'm going to teach you guys about standing waves, particularly for those that are within a tube or a pipe that is open at both ends. And what that means is you just have a pipe, a hollow pipe. If you were to cut it at both ends and just leave it like that, you have a tube or a pipe that is open at both ends. And the reason why we talk about this with waves is because with waves we talk about sound, and these open tubes would kind of represent instruments, and you can make different sounds, different pitches out of these tubes, and that's where we kind of relate all this back to. And so we're going to actually kind of come back to the wave speed equation. Now with these standing waves, you may have heard of different kind of fundamental frequencies, or this first harmonic, second harmonic. We're going to kind of get through that and then, like I said, relate it all back to the wave speed equation. So we're going to begin by what's known as the fundamental frequency. And the reason why it's called the fundamental frequency is because it's the most basic standing wave that we can get. And in the case of an open tube or an open pipe with both ends, the fundamental frequency has one node, and that one node is right in the middle. And the way that we would draw the wave to go along with this, and keep in mind, for any tube or pipe, for the frequency to occur, for that instrument to make noise, we actually have to have our antinodes at the ends. So you would never draw a node at the end of a pipe unless it's a closed pipe, but I'm going to save that for another video lesson. If you have an open pipe, you need to have an antinode, and so we're going to draw our wave something like this for our fundamental frequency, where we have our antinodes at the open end and we have our one node right in the middle. This is known as the fundamental, or also known as the first harmonic. Okay, and like I said, we're going to relate this back to our wave speed equation. And so our wave speed equation looks like this. The wave speed equals the wavelength times the frequency. And with these physics problems, usually what they're asking you to do is to solve for the frequency that the instrument is making. Okay, and so to solve for the frequency, we rearrange this equation, divide by the wavelength. Okay, and so our equation is going to look something like this, where our frequency is equal to our wave speed divided by the wavelength. Now, the way that the wavelength is determined is by the drawing, and it's always relative to the length of the pipe. So if we were to isolate one of these waves that I drew, okay, let's take this one for example. I'm going to put it in blue. If I take this wave right here, how many wavelengths is that in relation to the entire pipe? Well, you should notice that it's only half of a wavelength. And so what we would have to do essentially to get one full wavelength is we would have to double this pipe so that we could draw one full wavelength. Okay, if I were able to do that here, essentially, here I have my crest of this blue one, here's my trough, and then here's my crest. So right, crest to crest gives me one full wavelength. And so we're just going to relate that. Our wavelength is equal to twice the length of the tube. Well, now that I have this equation, I can substitute this 2L for my wavelength, and we would consider that to be the fundamental frequency, or the frequency of the first harmonic, is equal to the wave speed divided by twice the length of the tube. And so that's how you may have seen this equation. That's how we get that equation. is by taking a look at the standing waves inside the length of the tubes. So let's continue drawing some of the rest of these two tubes here. With the fundamental frequency, or the first harmonic, we had one node. So for our second harmonic, we need to have two nodes, right? And so that's going to be our pattern. Each harmonic is just going to add one node. So we get something that looks like this. And so in this case, as we begin to relate the wavelength to the length of the tube, just like we did up here, we see that in this case we have that one full wavelength. So I'm going to isolate this bottom one right here. So we have our trough, we go up to our crest and come back down to our trough. So that's one full wavelength for this length of the tube, and so we can derive an equation that our wavelength for this case is equal to the length of the tube. And so our second harmonic, the frequency of our second harmonic, is equal to the wave speed divided by the length of the tube. Okay, and so there's actually two, for each of these there's always two names. This is called the first overtone, or known as the second harmonic. Okay. All right, one last one. So once again, we're always adding one more node. So for our last picture, we're going to have 3 nodes. And remember, for these pipes, always have to have an antinode at the end of the pipe. So it's going to look something like this. And one more time, we're going to relate, kind of relate the one wavelength. So I'm going to go start down here for my trough and come up, and then come back down for this trough. So there's my one wavelength right here. And we see that that doesn't take up a full length of the tube. In fact, that takes up 2/3 of the tube. So our wavelength is equal to 2/3 the length of the tube. And so we can substitute that in for our last equation that we're going to look at, which would be V over 2/3 the length of the tube. And so we call this the second overtone, or the third harmonic. And then you would use these equations, obviously, to calculate the frequency of the first harmonic, or the second harmonic, or the third harmonic, or whatever the problem is asking you to do. Okay, so hopefully this lesson has helped you to kind of understand the differences between the different harmonics of the standing waves in a tube or pipe that is open at both ends. Hopefully it's helped you to kind of draw those waves, and hopefully it has helped you to kind of understand where these equations come from. So once again, thanks for tuning in to another lesson.